Today we're going to be looking at the third and final level of simplifying identities. At the top of your notes, you're going to see like a synopsis of the different identities that we have already developed. We will use sine x, cosine x, cosecant defined as 1 over sine, secant defined as 1 over cosine, tangent as sine over cosine, cotangent as cosine over sine, and then we also have our 3 Pythagorean identities, which we can rearrange as needed to shorten or sometimes expand, which is what we'll see in this lesson. One of the things that's different in this section is we're not given just a plain expression. We actually have an end goal in mind. So if you take a look at this first example here, I have a left side equal to a right side. Back in the day, identities looked more like 2 plus 3 equals 5. It's something that we know to be true. The goal would be to take the more complicated side, use legal algebra to simplify, and prove that both sides are in fact the same. I use the ditto symbol to represent the side that I'm not changing. But notice I'm only working with one side at a time. That's key. So if we start here in example 8, the first thing we're going to do is we're going to choose the more complicated side, which is going to be this left side. Our goal is to work with that until we get to sine of x. Given 2 sets of parentheses, I would recommend probably foiling. From here, I'm going to take all of these back down into sines and cosines. Since I have 3 different trig, none of them are squared that I can use Pythagorean identities with. Now, when you look at this, it looks very complicated, but notice it's one term. Here's the second. Here's the third. And here's the fourth. There's 4 separate terms, which resulted from our FOIL that we did initially. Now, if we look at this, the denominator is sine, denominator is sine, sine, and sine. I already have my LCD. So since my denominator for all of these is sine of x, I can go ahead and write it as one fraction. These middle terms will cancel as they are opposites, which leaves me with 1 minus cosine squared x over sine x. The top is an example of a Pythagorean identity. So again, we go back up top here and we rearrange this by moving cosine to the other side, it simplifies down to simply a sine squared x. We can reduce, and our final answer is sine x. Now, moving on to example 9. Example 9, you might be inclined, because these are not in terms of sine and cosine, to go to sines and cosines. There's a very simple way to do this problem, and it's a strategy you want to keep in your back pocket. The idea here is that cotangent and cosecant are related. They're related up here by the Pythagorean identity. If I take cotangent squared and replace it with cosecant squared minus 1, all of which is over 1 plus cosecant x, I'm a lot closer to having a top and bottom that looks similar. Pythagorean identities often come down to difference of squares and being able to factor further. This is an example of difference of squares. Cosecant x minus 1, cosecant x plus 1, all of which is over 1 plus cosecant x. Cancel the entire quantity, and that leaves me with cosecant x minus 1. Example 10, we're going to use a strategy called splitting the fraction. We can only split the fraction when I have a single term in the denominator. So to split the fraction, I'm going to turn this into tangent t over sine t plus cosine t over sine t. Cosine over sine is cotangent, so I'm already a lot closer to what I see on the other side. The question is, does this become secant? So this reminds me of the first assignment that we had in Delta Math. Take the top, turn it into sine t over cosine t divided by sine t. Remember to multiply by your reciprocal. This is gone. The sines cancel and it leaves me with 1 over cosine t plus, we can bring this down here, cosine t over sine t. By definition, cosine t, 1 over cosine t, is secant t, and cosine t over sine t is cotangent t. Now let's look at the last one. A lot of students balk because there's a lot of fractions in this problem. But remember, these are puzzles. They are true statements. They are designed to fit together and be able to work itself out. I think it's clear that this is the more complicated side. This is going to be a method using LCD. So what is our LCD? Our LCD is going to be the quantity 1 plus cosine theta times sine theta. What am I missing from the first? So sine theta, 1 plus cosine theta. What I'm missing is, in the bottom, to get my LCD, is a sine theta over sine theta plus cosine theta times sine theta. What am I missing to get my LCD? I'm missing the quantity 1 plus cosine theta. Now I have the same denominator. Up top, I'm going to leave this in the factored form, sine theta, 1 plus cosine theta. Remember, this is my LCD. Up top, I have a sine squared theta plus, now I'm going to distribute here and here, cosine theta plus cosine squared theta. Now, if you remember in addition, up here I'm going to give you an example. A plus B plus C is the same thing as A plus C plus B. So I can rearrange this or look at it and say, look, I have a sine squared plus a cosine squared, which is an example of a Pythagorean identity. That blue box is going to be replaced with a 1 plus the cosine theta. In the bottom, I still have sine theta and a 1 plus cosine theta. So this blue wave, if you will, is replaced with the 1. 1 plus cosine theta, 1 plus cosine theta gives me 1 over sine theta. And 1 over sine theta is cosecant theta.